So here's my second spring break video for Honors Pre-Calculus, and we're going to talk about logistic growth, which some of you have already heard of. Logistic growth is what you use when you are looking at data that seems to grow exponentially and then seems to stop growing exponentially. At first, the data really seems to fit exponential growth. So you're starting to see this orange dotted curve, how nicely it lines up with the blue dots. But then something changes and your data starts behaving more like exponential decay, heading towards some asymptote. How do you reconcile these two things? You reconcile them with a graph that shows both behaviors. And this graph is called a logistic graph curve. It starts out looking like logistic growth here with your blue data points, and then it switches to exponential decay. It starts out looking like exponential growth, then it switches to exponential decay at some point. That point where it switches is called a point of inflection, and that's an important concept for calculus later in other types of graphs. But the main thing in general, a point of inflection, which you learn in calculus, is the point when a graph switches from smiling to frowning. Logistic growth always starts out with a smile pattern, and exactly at the point of inflection switches to a frowning pattern. Won't always be exponential growth and decay, but if a graph switches from smiling to frowning, that is called a point of inflection. Okay, so that's enough in general. What does this specifically look like? Well, some very clever people figured out that logistic growth could always be modeled by this particular function here. And the only difference between these two expressions of the function is whether you use the function notation or A for amount again, because all of these exponential growth, decay, and logistic models are all about the amount of something that you wind up with as time passes. This part on the top, C, okay, this describes a horizontal asymptote, and another way to look at that is to use this notation we used before, this limit notation, and the limit as time approaches infinity of this logistic graph is the C on top. That is also called in biology a carrying capacity. One of the most common uses for logistic growth is how a new organism or animal in a new environment, how its population will grow. And eventually, there's some upper limit on that environment's ability to sustain whatever organism or animal we're talking about. So that's your limit to growth. It's the limit as time approaches infinity. Now, it's not really the limit as time approaches infinity in real life. In real modeling situations, something changes. Climate change changes a habitat. People come through and build houses limiting the amount of habitat for, say, in our region, deer, whose population would pretty much grow exponentially in the absence of predators or habitat degradation. But what happens is, as t gets larger and larger, this is a negative exponent. So the larger t gets, the closer to 1 this gets, because we start getting to negative infinity, but it's a negative exponent, so it's 1 over. So this whole thing starts to go away, and you're just left with c over 1. That's the only thing that's left. We'll talk more about how limits have that effect. So we have the carrying capacity, and A, B, and C are constants. And we'll talk a little bit more about what they mean. This B here, that's kind of like your K in y equals CE to the KT. So let's jump right into an example. And for this example, let's use one of these logistic equations. Okay. This function describes let's make that a little bit bigger, see if that's easier to read. This function up here describes the number of people who will contract the flu as it spreads through a town with 30,000 inhabitants. So 30,000 is the carrying capacity of this flu in this town. Flu can't inhabit more people than the town has. So that's your upper limit. Sometimes the question, what is the carrying capacity, is that easily answered. Now, how many people became ill with the flu when the epidemic began? Okay, well, when the epidemic began, what we're saying is that's when t equals 0. So if we take 30,000 as our numerator still, put that over 1 plus 20e to the negative 1.5 times 0, well, that's 30,000 over 1 plus 20 e to the 0. So that's 30,000 over 21, because e to the 0 is just 1. And then 1 plus 20 is 21. So all we need is that number. And what we're going to do is go here and take 30,000 divided by 21. And then we're going to remember that this software doesn't recognize commas. It thinks they're decimals. And so that is 1,428.571. So when time equals 0 in this case, there were, okay, now this is people, by the way, and for this estimate we're going to round up, so that is 1,429 people. You can't just be a tiny bit infected with something like the flu, so it's definitely going to be a case where you always round up, even though that one we would round up anyway. Okay, so if you're wondering what happens at the beginning of a logistic growth situation, you plug 0 in for t, work out that math. Next part of the problem isn't that different. How many people were ill by the end of the 4th week? Well, at the end of the 4th week, time describes the weeks, so all we do is plug 4 in for t. 1 plus 20e to the negative 1.5 times 4. And let's see what that is. So now we take this, let's get rid of that bit of silliness, and let's change its denominator to 1 plus e to the negative 1.5 times 4. Did not like my writing of 4, so let's try it again. Still doesn't. Let's see. Get rid of that. Okay, wow, this thing's really taken me a little while to like my handwriting. Okay, so after 4 weeks, we are pretty close to that 30,000 limit. We have 29,925.8, or as we're going to call it, 29,926 people. So we're getting very, very close after 4 weeks to that 30,000 person carrying capacity. Speaking of which, that's going to be the answer to part C. Sometimes it is that simple. What is the limiting size of f of t, the population that becomes ill? That's just 30,000. The limiting size is literally your carrying capacity, which is always your numerator in logistic growth. So these aren't that tricky. This book sticks pretty much to these uses of it. You don't have to go searching for the point of inflection. That's a little different. But we'll do one more of these just to make sure it's clear. In a learning theory project, psychologists discovered that a function with 0.8 on the top divided by 1 plus e to the negative 0.2t is a model for describing the proportion of correct responses after t learning trials. So what this describes is if you're trying to teach someone something, okay, how long do they start getting it right? And how often do they get it right? So, for example, how often, if I quizzed you guys on this exact lesson immediately, how many times would I have to repeat it before you started getting it right? Okay, so not sure if this model really applies to learning math in this class, but let's see how that looks. All right, so find the proportion of correct responses prior to learning trials taking place. All right, well, that means right before learning trials started taking place. So again, they're asking us to find f of 0. What were the test subjects like the second they walked in the door? So all we do is 0.8, 1 plus e to the negative 0.2 times 0, which is 0.8 over 1 plus 1, which is 0.8 over 2, which is 0.4. So we should expect 4/10 or 40% of people to be able to do this skill or trick right when they walk in the door. Don't know what learning skill they're talking about. Most math students can't really do anything right when they walk in the door, so I don't really think this applies to what I do for a living, but hey, let's see what they say in the next ones. So, part B, find the proportion of correct responses after 10 learning trials. Okay, so after you go through 10 attempts to teach someone something, what proportion of the group should get it right? This is just a matter of finding f of 10, or what happens when we put 10 in for t, and what that will get us is, this thing's still messing up. All right, so I'm going to put in negative 0.2 times 10. Really didn't like that. Doesn't like that second decimal there. This could take me a little while. Tell you what, I'll do the easy part first. Put the 0.8 up there. And now, doesn't know what to do with those. Okay, let's see if we can just sneak this 10 in here. Somewhere, someone, probably Joey, is shouting just right negative 2 up at the top, and stop trying to make this work. So I think at this point I'm going to take that advice and just do that, since I happen to know that 0.2 times 10 is negative 2, and this gives us 70.4 as our proportion. That seems reasonable. Whatever the skill is, 40% of the people walk in knowing how to do it. 80% is the maximum you're going to get because your carrying capacity is on top. So after 10 tries, it looks like 70.4% of the people in your trial should be able to do whatever skill you're trying to teach them after 10 tries. So that is 0.704 or 70.4%. And I've already answered part C, but let's write it out just to be sure. And let's see, that's not what I intended to do there. I meant to, whoa. Okay, let's try this again. There we go. What is the limiting size of f of t, the proportion of correct responses as continued learning trials take place? Whatever this particular skill is, the answer is 0.8 or 80%. So whatever the skill is, you're not really expecting more than 80% of your target class or audience or students to be able to perform it, no matter how hard you try. There's 20% who just won't ever get it. All right, well, that's it for logistic growth. This should allow you to do the homework, which I'll post, and looking forward to seeing you guys all again in virtual classrooms on Tuesday next week. All right, be safe. Take care of each other.